So if you remember, last week we ended the lecture by discussing the advantages of cross-laminated panels, or X-lab, or also CLP, how they are called. Again, just to have a look, this one's better. And this is another one. You want again to touch with your hand. 1, 2, more or less the same. So, advantages. Remember, just now repeating what we said last time. First of all, we have a panel which is more isotropic compared to Lula. So, more isotropic in plane. So, in plane we have similar properties in both directions, as opposed to glue-laminated timber, where we have a good property in one direction and, let's say, a bit worse property, but actually much worse in the other two directions. Greater in plane stability. So, while glue-lam is going to shrink mostly in the blue direction, X-lam is going to shrink only in the blue direction. So, in plane is a much more stable product, so can be used with much better application for 2D structure, 2D elements like plates and walls. Possibility to use low-grade timber. So, since each defect is less critical compared to glue-lam, so we can use low-grade timber in this kind of product here. While instead in glue-lam, a defect is much more critical on the strength of the beam. And then, if you remember, this was quite an interesting property. Reduced splitting tendency, connection region. We said that if we basically place a dowel on a timber, on a glue-lam beam, and then we pull, in general we will get some kind of secondary stresses. So the idea is that if this is, let's say this is the glue-lam, we do a hole, and then we pull in this direction, we have a distribution of secondary stresses. If you do an elastic analysis of a plate like this, you will find that there are some basically secondary stresses in the tension direction that are going to act perpendicular to the grain. So in a glue-lam like this, the failure very likely would be due to the formation of a crack. So you see this red line shows a crack which forms on the dowel and then progresses up to the end. So we have a failure due to secondary stresses, tensile stresses, because we said glue-lam is very weak perpendicular to the grain. Instead, if we have a cross-lam panel, of course, in a cross-lam panel we have some boards in this direction, which may split, but immediately underneath we have some boards in the perpendicular direction. So this, if we do a hole here, these secondary stresses, they are acting perpendicular to the grain on the first layer, but parallel to the grain on the second layer. So this second layer is going to provide, if you want, an intrinsic reinforcement to the panel. So in this case, we may have like a splitting only on one layer, but for sure not on the other layer, because those are secondary stresses, they are low value. Usually we know a problem like this in a steel, for example, a region, if you do a steel structure, we never check the steel for secondary stresses. Why? Because steel is homogeneous, isotropic. So those stresses here are always much lower compared to the stresses in this direction, because those ones are secondary stresses. We learn that the strength in this direction is almost zero, it's 1 megapascal, while in this direction you get 20, 30, 40 megapascal. Okay? Good, so this is very important. And for this reason you can see here, when we can expect important secondary stresses also in a beam element, it may be a good idea to use cross-lam, because for example in this case you see there is a plate, there is like something hanging here, and of course you get again the secondary stresses perpendicular to the grain. So you may get, you see this splitting here. So in this case you should use some reinforcement like screws or plywood plates glued or nailed to the surface of the beam. Screws in Italian are viti, plywood is compensato strutturale, and nail means nails are chiodi, quindi chiodati, non chiodati to the beam. So in this case, to avoid those cracks, we need to use this kind of reinforcement. Instead, if you use X-lam is inherently reinforced by the layers that are running perpendicular to the grain. So we don't need, in this case, you see, if you have, for example, a beam with a notch, or a beam with a load hanging underneath, or a beam with a hole, if you use X-lam, we don't need to put any reinforcement because the secondary layer are already acting as a reinforcement for the beam. Okay? So this is another important advantage of X-lam. Now let's go to have a look to the disadvantages of cross-laminated panel as related, or if you want, in comparison with glue-laminated timber. First of all, we need a larger volume of timber. So in general, we need to use more planks, and so it may become more expensive if the unit cost of timber is high. So if the plant is expensive, then of course we need to spend more money because we need more volume, an increased number of plants. However, low quality wood can be used. We said before that we can also use low quality wood because the presence of timber is not so critical as for glue laminated timber. So we can also think about using wood that otherwise we would just throw away. Very low quality wood that otherwise we would just use for example, as a firewood, can also be used for cross-laminated panel because their defects are less important. Second disadvantage, reduce strength in the main direction. We already discussed it last time, if you remember, because only the board loaded parallel to the grain carry the load. So, for example, you see here, this is a typical gross cross-section of a cross-lam panel. So we have 4 layers running outside the section. So with the grain, the grain running outside the cross-section, and 3 running in the perpendicular direction. So of these 7 layers, only 4 basically are resisting this plane, and therefore are only the one with the grain parallel to the direction. The other 3, being loaded perpendicular to the grain, they have a much lower module of elasticity. If you remember, it's almost 1/30th of the module of elasticity parallel to the grain. So they hardly carry any load. So the other one are almost unloaded. When it comes, if we use this panel, for example, as a beam. So this means that if we were using a glue laminated timber, we would have used only basically 4/7 of the total volume of timber. Because 3/7 are plants that are not used in the main direction. So we have to, again, with this kind of product, we need to use more wood. For this reason, sometimes this common layout, where we have, let's say, an odd number of layers. So we have, for example, 2 layers in one direction, 1 in the other, or 3 layers in one direction, 2 in the other, or like here, 4 layers in one direction, 3 in the other, so an odd number. Often this odd number has been changed to a different, for example, an even number, like here, and also a different thickness of the board used perpendicular to the grain. You can see here in this case, in order to minimize this reduction in strength, the idea is to use 4 thicker layers in the main direction and only 2 thinner layers in the other direction, the direction which doesn't carry any load. In this case, we can save some material again. Because as we said before, those perpendicular layers are mostly there to stabilize in some way the product. So to make the product a little more isotropic and to reinforce, as we said before, to reinforce the panel perpendicular to the main direction. This means that when it comes to applications like this one here, for example, double taper beams, so travi rastremate in Italian, or beams with holes, why do we need some time to drill some holes into the beam? What do you think? Why do we need some holes?
Connection.
More than connection, it's services. Like heating systems, nowadays we have lots of service inside our building. So heating systems, system, air conditioning, more than electricity. So the heating system and air conditioning are the one with a larger size of the pipes. So, of course, it's much better to have a hole here, because otherwise we would have to put the pipe underneath, so that the thickness of the floor will be much more increased. So often we need to do some holes. Now, the problem with the holes in a beam, in a timber beam, is that the holes will in some way weaken the beam, mostly because, if this is, for example, cross-laminated, this is a glue-laminated beam. If you do a hole like this, you can expect some stress concentration on the corner here. So you have some stress concentration, and so it's very simple here, it's very often you get a crack formation. So this kind of discontinuity point, if you do, for example, if you were to do an elastic analysis of a system like this, you will find here that the stress will tend to infinite. Never goes to infinite, of course, but this means that it's very easy here that a crack will form. And then as the load increases, this crack is going to progress. And of course, this crack is not something which is not very nice to have, because it's going to separate the beam into portions. And so then you don't have here, when you do, for example, a bending verification, you assume that here you have only one piece of wood, only one cross section. Instead, here in the reality, you have two cross sections, which is not the same as having one more cross section. Okay? So for this reason, beams with holes, but also beams with notches. Also here again, we have a corner. And also here, you can expect a crack formation. So in this kind of beams here, it may be a good idea to use cross. Why would it be a good idea to use cross? Because of course it's true that we have to use a larger cross section, as we stood before. We need more wood, but on the other hand, we don't need to put any reinforcement, because actually the reinforcement is already in place. Are the secondary layers surrounding perpendicular to the break. Also here we will study later on, also in this kind of taper beams, we will see that there are also here secondary stresses. So there are tensile stresses around here. So also in this case, it's a good idea, to use the cross lamp rather than glue lamp. If you use glue lamp, we need to reinforce, to put some screws or some epoxy bars or some plywood. In this case, instead, we don't need to put any reinforcement. Okay? Okay. Any question with Prof? I think it's very important to understand the advantages of the material. Because this material here, cross lamp, now is being used much more than in the past. I could say that most of the medium to high-rise timber buildings that we build right now, they're made of cross lamp. While in the past, they were not made of cross lamp, they were made of glue lamp or other material. But today, nowadays, cross lamp is much more used than in the past. I would say it's probably the most important product at the moment. Okay, cross lamp and glue lamp. But cross lamp is very much used. So it's very important to understand the advantages and also, of course, the disadvantages. Okay? Any question? Okay, so if everything is clear, now we move to LVL and plywood. So LVL is an abbreviation for laminated veneer lumber. Laminated, you know what the meaning. Veneer is basically the name for this kind of material here. So this one is called a veneer of wood. After I will pass you around to touch it. So this is a veneer of wood. So laminated means that it is in some way laminated together by gluing. Veneer is this. Lumber is a kind of Canadian name to say timber. Canada and North America, they call it timber, solid timber, they call it lumber. Okay? So laminated veneer lumber, LVL. In Italian, we use LVL, but we translate it into microlamellare. So, we said LVL, microlamellare, plywood in Italian is compensato strutturale. It's basically this material you can see. It's called plywood compensato strutturale in Italian. Very similar to what we call compensato marino. Some of you might have seen compensato marino used for some boats. Similar kind of material used to build some boats, also boats for rowing, but also normal boats. Okay, laminated vinyl lumber. Let's see if I have a small specimen of it. Laminated vinyl lumber, so this one. And plywood, this one. Okay. Then touch it, and use it. So LVL and plywood are products that are conceptually very similar to glue lab and cross lab, respectively. Okay? The main difference between those two products and the other two that we saw before is the thickness of the material which is glued together. In one case, for cross lab and glue lab, we glue together boards of thin boards which are usually between, let's say, 20 and 40 millimeters thick. In this case, instead, we glue together veneers which are 3 millimeters thick. Okay? So we start from LVL, laminated vinyl lumber. You see the production process. You have the whole trunk. The trunk is debarked. So first of all, once we get the log, first we need to get rid of the bark, scortecciato. After that, you see this one. It is rotary pin. So the whole trunk is rotary pin. Here we have a shape, which basically, and there is another machine making this to spin. So this one is going to spin this way, very fast. And there is a blade here. So in, let's say, about 10 seconds, this log is transformed into an endless veneer. Exactly like the comparison we said last time with toilet paper. You know, toilet paper, you make it to run, and then you get this endless veneer. So the veneer is basically this kind of thing. So this thing, originally, you see, this one was basically in the trunk. This was rounded in this way, and then this is built, it became in this way. Now I will also pass it to you around, but the very interesting thing to notice is the different thickness of this. In this direction, you can see it's thick. Well, sorry, the stiffness is stiff. In the other direction, it's not stiff. And of course, then also the direction perpendicular to the grain is not stiff. Why? Because again, this is the direction of the grain. The direction of the grain is very good, the property. The direction perpendicular to the grain is very poor. Okay? So the idea is that we have this, we produce from each log this endless veneer, then we cut it into small panels, and then we reglue them together. You see rotary pin lathe, veneer, cut, dryer, then the grading, glue spreader, pressing, and at the end we have this product. So the idea is that some of this, we are going all of them to glue together, all in the same direction, okay, in a parallel direction. So the result is this. You have it now. The result is this LVL, which is very good and stiff in the longitudinal direction, and of course, perpendicular to the grain is very poor. So we get a highly anisotropic product, like timber and like glue. Okay, because all the veneers, they are all glued together in the parallel direction, in the best direction. Of course, again, this concept, you can see here there used to be a knot between here. Now there's nothing anymore because the knot is gone. Here also there was a knot. Perhaps at the beginning they were here. After the production, they are just glued in a random way. So rather than having a knot just going through the whole thickness, now we have a small knot here, not a small knot there, and so on. And so the effect of the knot on the global behavior of the material is negligible.
Because of the thickness of this.
Because of the thickness. In fact, this 3 mm thickness is not a random value. Yes, it was studied. Basically, they found out that with 4 mm, we still have an influence. With 3 mm, no influence. 2 or 1 mm, no influence at all. So they decided, okay, 3 mm is the best thickness. Because of course, with this product here, it's a very rich of glue, as you can imagine. Because we have 3 mm, in order to get to 30 mm, you have to glue 10 of those, so you have to use lots of glue. And the glue is not something, it's a product that's, ideally, particularly if you talk with the bioarchitects, they don't like to have any glue in the wood that they are using. Of course, glue is also expensive. So, but again, if you want to maximize the strength, so to minimize the effect of the knot, 3 mm is the best thickness. Okay? And as we said last time, LPL, we have almost as clear wood. So in the end, basically we could get rid of the defects with this material. The property of this material is like the property of a clear specimen without any defects. Okay? Just remind you, see grade timber, the probability density function, grade timber, Euler, LBL. So LBL is about the most reliable one. And because you see the Gauss, the normal distribution is with a smaller standard deviation. The mean strength, they are almost the same, but of course, since the standard deviation is lower, the characteristic value of strength is much higher for LBL compared to Euler and graded timber. Also here you see starting from a base material of, let's say, 10 megapascal. Once you laminate into Euler, the 10 becomes 20 and the 20 becomes 40. Module of elasticity is said to from 6 to 8, from 8 to 13. So as you can see, roughly speaking, to go from some timber to Euler, we can double up the strength, and from Euler to LBL, another doubling up. So at the end, from some timber to LBL, you have 4 times the strength. The young module does not improve as much as the bending strength. So 6, 8, 13. So more or less, from solid timber to LBL, you can double up the young modulus, but you can increase by 4 times the strength. Okay? In fact, one of the problems with LBL is that very often the design is not governed by strength, but it's almost always governed by serviceability instead. So excessive deflection, or sometimes problem with flexural torsional buckling, or just flexural buckling. So here is a production process. You see this kind of these veneers are graded. And of course, LBL, it's a highly anisotropic material. It's very anisotropic. It's an excellent property in one direction and very bad in the other. So it will be mostly used for 1D elements. So basically from joists, purlins, rafters, beams, and columns. Just some wording here. Beams and columns, you know, in Italian it's trave colonna. Rafters, there is no translation in Italian. It's a beam, it's a kind of beam if you want, rafter. Perhaps not the main beam, the secondary beam. Purlins are the arcarecci in Italian. And joists are the smaller beams that you use for a floor. So for a floor, usually if you have a one-way, two-level system, or let's say a three-level system, you have the decking, tavolato, then you have the joists, travetti, and then you have the main beams or rafters. Okay? Again, we said excellent property is the red direction, much worse property than the two blue directions. Here are some mechanical properties for LDL. For LDL, there are some correction factors for strength. You see this KH. Because basically for LDL, the reference depth in bed is 300 millimeter. If your depth is different from 300 millimeter, then the characteristic strength should be multiplied by this factor here, taking into account the different value of the height of the depth. Also, for tension, the reference length is 300 millimeters, sorry, 3000 millimeters, so 3 meters. If you have members which are shorter or longer, then you need to multiply the strength by this size factor here. Okay, so we said before, by feeding the log and by gluing together those veneers, we can get a DL. So this would be basically a DL. So very good in one direction, very stiff in this direction, and very good in the other. Okay, mostly used for one-dimensional members. Now, if we have to use this material for two-dimensional members, like a sheathing, so polymer, for example, for a wall or for a floor, of course, LDL is not good. It's not good because it's good in one direction, very good in the other. So the idea is then to do more or less what we have done for closer. So, for example, instead of gluing all four veneers in the same direction, we can think about gluing one perpendicular, the other one perpendicular. If we do something like this, you can see that immediately we get a much more isotropic material. Immediately. So basically, plywood is based on this concept here. So some of the veneers are rotated by 90 degrees in order to create a product which is more isotropic in its plane. But plywood is almost isotropic. It's an almost isotropic product in its plane. Okay, now I'll give you this one so you can play a little bit. Just be careful because in the direction perpendicular to the brain, they are much weaker. So don't force too much because otherwise you see this is a piece that was forced a little bit too much by some of your colleagues and now I have one piece here, one piece in the other. Okay? Here is again the production process, very similar to the one we saw already. The only difference being that we need to remember at a certain point we need to rotate by 90 degrees. Otherwise we get a DL. Okay? That's the only difference. Some application, we said plywood is mostly used for two-dimensional members. For example, you can see here this is a wall, a shear wall. On the inner side, you can't see, but on the inner side there is a frame. So you see there is a stud, a vertical stud in this way, there is a vertical stud here, there is another stud in between, and then there are some horizontal plates. So this sheathing of plywood is basically nailed on this frame in order to get this shear wall. This kind of construction system is called light frame system. Sistema a telaio leggero. And later on we will study much more extensively the strength of this kind of system. Okay, light frame construction. Plywood can also be used for the floor, the deck of the floor. You see here, there are some joists, cavetti, and on top of the joists, rather than using planks like in the past, we are using this plywood sheathing. Usually they comes in the size of 1.25, so the breadth is 1.25 by 2.50. This is the size of this panels. Then there are other products, like particle boards. Particle board, in Italian is called truciolare, or pannello di particelle, is basically obtained from wood particles mixed with glue. Heated and compressed. So the idea is that I'm going first to destroy the microstructure, if you want, of the wood. I'm going to transform that microstructure of the wood into a number of cells, and then I'm going to mix the cells with the glue, and I'm going to press them together. In this case, the product that I'm going to obtain will be a product which is fully isotropic, because the cells are basically glued with a random direction. They are not all like in the wood with the same main direction parallel to the stem. They are random oriented. So the product that we get in the end is homogeneous. So it's of course homogeneous and isotropic. So the advantages are isotropy, dimensional stability, less calculomechanical properties. However, there are also some disadvantages. First of all, less strength. So you see the bending strength is 17 megapascal, it's not a lot. Less stiffness, only 4 gigapascal. Why so low stiffness? Because they are mostly made of glue. So they are made of course, wood particle, but lots of glue. So the glue doesn't have a high module of elasticity. So the module of elasticity is very low, and also greater creep. Also lots of creep because the glue is a viscous material. So we can just expect to have lots of creep. And very bad behavior if in contact with water. You probably know particle body, use particle body in the past or something to do something. If it comes in contact with water, then you can actually throw it away because the behavior is very bad. So this is the system we're talking about, particle boards. I would say that we should never use particle boards in our construction. I know in England, also in New Zealand, they are used for the flooring, but I would say in Italy, I wouldn't use this kind of flooring because it's a low quality. And this is plywood. Much better to use plywood than particle. It costs more, but the properties are much better. And then we have oriented strand board, OSB also. In Italian we also call it OSB, where you see there are some not the fibers, we have some pieces of wood that are basically all glued together, all oriented. We said before there is often you can see this to use in the fences of the building sites. Also here, if you go outside, you will see that this is being used for one of those buildings on the right hand side, all around, so you can see this oriented strand board. Oriented strand board is a better property compared to particle boards, and I would say worse compared to plywood. It's being used quite often. It's used quite often in our country for light frame construction. So if you do these walls like this, I will tell you before, this one, very often we use in Italy oriented strand board instead of plywood. Now some picture, some example. You see this is for example an LVL beam here, LVL beam here, all around. Some other beams or rafters made of LVL. All these figures, all these pictures were taken in New Zealand. This is a roof where you see the post or colonna here is made of round wood. Sometimes we use round wood, which means that we have our tree. We get rid of the bark or texture. In the end, we use the whole pole. You see, sometimes outside, for example, for the lights, for the electricity, use the whole pole. Also construction application. So this is a round wood, and then here you have the beam. This is basically a portal frame made of MDL with some rigid joints here. Again, this main beam is made of MDL, and here other application with MDL. Then we have this application, which is not common in Italy, it's more common in other countries, in America, in New Zealand, also in other European countries. This kind of high joist. So the idea is that to try to optimize the cross-section of a beam, you know that the optimal, one of the optimal shape for a beam is the I shape. Because in this way, you get basically the web, which is the main function of the web is to carry the shear force, and then you have the two flanges, where the main purpose of the flanges are to resist bending. So in this case, you see the two flanges are made of LDL, and the web is made of plywood. Then these joints here are glued joints, as well as this vertical joint. They are all glued together. Some application, this I joist here for a floor. For the purlins, for the arcarecci here, of a roof. And some other application. Of course, those are quite simple to for having some penetration for the surfaces. The idea, of course, we should try to do these holes in the parts which are less stressed. So theoretically, you shouldn't do this hole on the web very close to the support, because we know very close to the support, particularly on the middle fiber here, we have the maximum shear stress. Okay, so don't go too close to the support, and of course don't touch the flange, because the flanges, they are carrying all the bending moment. Okay. There are some special joist anchors. You see here, this is a combined construction. We have a main beam made of steel, and then these joists here are made of wood. So there is this kind of joist anchors that are fixed on top of the steel beam, and they are needed in order to basically support the joist made of LDL and the planking. Now, some picture of some application, nice Gulam structures here. Okay, first of all, this you can see is nice 3-inch arch made of Gulam. So we have one inch here, 1 inch here, and 1 inch on the other side. So the structure is statically determinate. The hinges are physical hinges made of steel, basically, bigger dowel. The shape of the arch you see is not constant, so if you look at the depth is not constant. We have a larger depth here, more or less in between. So these are the main resisting structure in the transversal direction. Then there are a number of purlins connecting all these arches. And then you can see at a certain point here there are some steel bars. Now, what does those steel bars carry? So why do we use some steel bars here? What's the function of those steel bars? Buckling of what? Okay, so the first purpose of those bracing, these are called bracing, it's the bracing system, is to basically avoid the buckling of the arches. That's correct. In fact, those crosses makes those points here as a fixed point in terms of buckling. So the lateral resistance here is restrained. So when we are going to discuss about lateral torsional buckling, we will have that the distance, the reference distance, will be the distance between this point and this point here. Without those crosses, the reference distance will be from here to the other side. And we will see when we do a calculation of a timber beam, we will see that without this restraints, there will be no way to get the lateral torsional buckling verification satisfied. Okay? So this bracing system here is really needed for timber but also for steel construction to provide some lateral restraints to the arches, to the main frame. In this case, the 3 big arches is the main frame of the structure. Okay? So the first reason is this. Second reason, what do we need also this bracing system from? So to prevent buckling, and then for lateral actions. Yes. So we need also as a bracing system. So which means to resist what kind of horizontal actions? Wind or earthquake. In which direction? Acting in which direction?
Perpendicular to
perpendicular to the axis. Exactly. So the out of plane horizontal forces, so that basically the wind forces and earthquake forces acting perpendicularly to the plane of the arch will be resisted by this bracing system. Okay? While instead the wind forces and earthquake forces in plane, so parallel to the 3-pin arch, will be resisted by what? By your what? What is the structural system resisting wind and earthquake in the direction of the plane of the arch?
The arch itself.
The arch itself. Okay, the arch itself is a 3-pin arch, so it's a statically determined system. It can carry the loads also horizontal, not only the vertical loads. Okay? It's clear? You can also see that actually here, in this bracing system here, there is a doubling up of the purlin. So you see here, where there is the node between the, let's say, the arch and the two rods, there is one more purlin which has been placed here. So that you see that the purlins usually are on the extra rods of the arch, but in this case there is still one purlin on the extra, but there is another one here in the middle of the arch. So we have doubled up the purlin here. Why is that? Yes, because in this case the designer thought it was a good idea to have a different system for carrying the vertical load, the purlins, and instead to make the bracing. So here there will be a higher purlin there to resist the vertical load, and the lower purlin here instead to make the bracing system together with the arches and together with the bracings. Okay? It's clear? We will talk more about bracing systems later on, because as you can imagine, unlike a reinforced concrete structure, what we studied 1-2 years ago for some of you, where all the joints are rigid, here the system very often they may be statically, they may be unstable basically, because we very often use pin connection. So the bracing system is really needed in order to carry the horizontal loads. Now the remark is that we have one bracing system here. If you look at another bracing system here, 1, 2, and then nothing between. But since we have 2, also these arches in between, they cannot move too much. How can they move? Because they are connected, you see, with the purlins, with the other arches which are fixed. So this means that this purlin here are also important to make sure that the arches in between cannot move, because they are connected with the arches which are in some way fixed by the bracing system. Okay? Any question about this? Okay, now this is an example of a strange building. As you can see, where we have what they call a bifurcated ridge joint. So here we have basically a ridge beam, and then the ridge beam is going to have a kind of fork. You see, one beam runs in this direction, one beam in the other direction. So how did they do this joint here? What kind of joint should be this, in your opinion? Should be a pin joint or a ridge joint? So it's a cerniera oppure un nodo rigido? Sì, in Italia. Should be a pin or rigid. If you were a designer, how would you design this? Is it a pin connection or is it a rigid joint? Well, have a look. So this is a pin. Where is the part which is bearing this pin here? If you look here, the bar bearing this pin is this one here. See? There's one beam here, and then there's another beam here. And there are some columns here, there are 2 columns, 1 and 2. Okay? So this joint, how should it be, in your opinion? Rigid or pin? well, if this connection here was P, then the system would be basically probably labile. So it would be, unstable. So this joint here must be rigid. Okay? So how did they do a rigid joint? Look here. So this is basically the main beam, and here there are the fault, 1 and 2. In order to be able to transfer the bending moment, of course, if you want to design a rigid joint, you need to be able to carry the bending moment. How can you carry the bending moment? You need to connect basically the fiber which carry the compression with the fiber which carry the tension. So the idea was, you see, to basically to cut a hole inside here and to slot inside a steel plate with some holes. So this is the steel plates, these are the other two plates going in one beam and the other, and then the connection here is done using some bolts. So in this way you can transfer the compression force in one direction or the other, and then you can transfer also the tensile force to the bottom side. You see what they did? Final result, the bolts, and then in order not to see the bolts, to see nice, the nice appearance of wood, what they did also, they put some small elements of wood to cover this bolts. Also here they put some plates of wood, which are of course not structural, just to cover the hole, to give this nice appearance of wood. You see? Now, you don't see it anymore. This is the structure, how it was built. And this is another nice structure that was built in New Zealand for the local Maori community in Auckland. You see, this is the structure made of lula. Most of the elements are carved elements. You see there are some arches made of lula, which are then cut in order to get this cross section, circular cross section. Again, the connection is made with steel plates and bolts running through the steel plates. Also, some round wood was used, you see, to create this pillar in between. This is round wood. Connection always with bolts and plates. Connection again, you see inside here there is a steel plate going out this way, going out this way, with another part in this way here. And then the connection with bolts, pull on it. This is looking out from underneath. You see these steel plates where the beams are connected to. And some nice photo looking above. You see these elements completely carved. These joints made of steel plates and bolts. And this is from outside. Very nice looking from inside. And then just to conclude, the case of a dome made again with lula made with timber. You see here some arches made of lula and some elements again made of lula. Looking up, of course, if you have a bolt, you have to have some elements, the arches, which are mostly subjected to compression. Then you have these other elements, which are subjected, the top one are subjected to compression, and the lower one are subjected to tension. Of course, one problem is related to the fact that all these arches should converge to the same point. The problem is that these arches are not very slender, they have quite a big cross section, and so there is no room to get all the arches in the same point. So what did they do here to solve this problem? Here you can see better. So some of the arches, 1 and 2, they converge to this ring. The ring must be very stiff in compression. So this ring is made of steel. And then this other one, they are connected to a secondary ring, which is again is made of lula. So 1 and 2 converge to the center, 1 and 2 instead they are connected to this secondary link, which again transfer all the stresses into the main point. Okay. So now now that we know a bit more about the microstructural group, the macrostructural group, the properties, we know also the different kind of engineering group products, we can start now talking about design. So how to design a timber member. And we move to the next lecture. So in this lecture here we are dealing with design process in timber engineering. So what we want to do now, well, we will start with the objective of the lecture. Then we will have an introduction about the use of wood construction. And then we will have a list of advantages and disadvantages of wood as a structural material. This list will be useful to understand also in design what we need to be more careful of compared, for example, to structure like reinforced concrete. We will talk about ultimate mistakes, design action strength, and serviceability mistake, not style. So we said ultimate mistake, serviceability mistake, design deflection limits, and then we will end up with some tables for preliminary design. So after this lecture, you should be able, in the end, to design a simple timber member. We will see also a work example of design of a simple timber member, and then we will go to a work example a little bit more complex about a small roof, how to design a small roof. After that, there will be another long lecture talking about connections, so how to design the connection, and then you will be ready to start your design project. Actually, you will start your design project at the end of this lecture here, because you will start designing, for example, you could do the preliminary design and start calculating the actual, etc. So I will speak anyway with Dr. Somenta, because last year we realized that some of you were not very confident with using SAP 2000. So we had a lot of problems with, the office hours, lots of students were there saying we were not to use SAP 2000, not to do the modeling. So we were thinking perhaps this year to do during the lecture some real lecture about using SAP 2000. You have been using SAP 2000 with in reinforced concrete design, actually, but just for a plane frame, right? In this case, we have to use SAP 2000 to do a space frame, you will see. Because, of course, we will do some plane frames, but we will have to model also the actual perpendicular to the plane. So you will have to do a modeling of a space frame in the end. So perhaps it may be useful to do a couple of lectures, maybe with a computer and also you with your computer to follow some indication about how to do this model in order to say that. And then the idea, probably you were told, the idea is that ideally, since this year, finally after many years, we could get to a result that this is the only project that you should be able to follow right now. So last year we had this course in parallel with a course with Professor Cinuzzi, and then the students were busy 24 hours per day doing the project with Professor Cinuzzi. So so here I didn't have any time, students didn't have any time to do my project. This year, this should be the only project that you should be doing this semester. So the idea is that we would like you to do your project during the year, so right now, and when you do the exam, you've already handed in the project. Not like now, that I still have students bringing in the project when they have attended the course 2 years ago. Okay? So the idea you should do the project immediately, because this will also be useful for the exam itself. So I think that's as soon as I finish this presentation here, you are able to start doing some preliminary design of this. We will do basically one single story industrial building, swimming pool, and then there will be another little project at the end about a small building. But the most important project will be this one. So the idea is that you should be able to do the project during the year. So in this way also, if you have some doubts, you can clarify during the lecture and so on. Okay? So, the objective of this lecture, as I said before, is to review the design process of a timber structure according to the Eurocode 5 with regard to strength limit states, including uplift, and serviceability limit state. If you want, we need to see how we can apply the concepts that you learned in the previous structural engineering courses, which is basically only reinforced concrete design, I guess, because this is the first structural design course that you are following after the degree, the first 3-year degree, right? This is the first course. So basically we need to see how to change those concepts that you learn from reinforced concrete design in the case of timber. So we start as usual from very basics, use of wood in construction. Wood, of course, is used in construction with different applications. We have as a structural material, this is the application that we are most interested in this course. But can also be used for finishing. You see here for cladding, flooring, thermal and acoustic insulation. We have some wood-based panels used for thermal and acoustic insulation, doors and windows, furniture, and so on. So there are lots of applications of wood in construction. Of course, we are interested in the use of wood as a structural material in this course. Let's now have a look at what we can regard as advantages of wood over other materials. So, first advantage, aesthetical appearance and pleasant smell. Second advantage, sustainability, hygroscopicity, thermal insulation, tensile compression bending strength, high strength to weight ratio, and speed of erection. Yes?
Why hygroscopicity is an advantage?
Which one is hygroscopic? Well, you will see hygroscopicity is both an advantage and a disadvantage. In fact, later on we will talk about some disadvantages, we see again hygroscopic. Now we will see also why it's an advantage. It's an advantage for the well-being of the people. Now I want to show you like this. We are going now to spend some time to discuss all of them, just to see what we can say about this. So first of all, aesthetic appearance and pleasant smell. So wood is very often preferred by architects and by engineers, architectural engineering, and also from the clients to decorate a flat house. So the idea is that they like the appearance of wood, and so they said, okay, I would like to see a structure made of wood, so I can in some way do a kind of architecture using the wood itself, like the exposed wood. And also the wood is pleasing to smell. When you go into a timber building, very often you will realize that there is a smell on the wood. That's very general wood. So it's in some way, it's an advantage, this one. Okay? Now, sustainability. For sustainability, there will be a specific lecture that you will do with Dr. Someta, try to discuss about sustainability. So why is wood sustainable and, for example, if concrete is less sustainable? We could spend all the rest of our afternoon discussing about sustainability. I would say we just put 3 bullet points, and then you will discuss later with Dr. Someta about sustainability. First advantage, first reason why we may regard wood as a sustainable material is that material regeneration over rotation cycles of 25 to 50 years. What does it mean? It means that from when I plant the tree to when the tree is ready for harvesting, it takes between 25 to 50 years. So we can regenerate the wood over let's say, 25 to 50 years. If you think about other materials like oil or coal, this regeneration cycle, this rotation cycle takes much longer, it takes millions of years. So in this respect, basically, I would say wood is sustainable because you can produce new material over 25 to 50 years rather than millions of years. Okay? In other words, once you've used all the oil of the planet Earth, it will take some millions of years to produce other oil. Okay? There's no other way. Instead, with the wood, we can continuously produce wood over 25 to 50 years, which is not a lot. It's related to the millions of years that it takes to produce coal and oil. Okay? So the first reason why I would say wood is a sustainable material is this material regeneration. I don't know if any of you have some comments, but this is quite obvious. Second, reduce CO2 carbon dioxide emissions. Here it's a bit more complex, but the idea is that the wood, when you have a tree, you have a chemical reaction where basically the wood in some way stores the carbon dioxide of the atmosphere and produces oxygen. So we could say that a tree is basically a volume of carbon dioxide in the air. Carbon dioxide at first was in the atmosphere and then is basically embodied into the wood. Since now you probably realize there's lots of now discussion about the problem with the carbon dioxide, but most of the problem seems to be related to the fact that global warming in some way is related to the concentration of carbon dioxide in the atmosphere. So there is a very strict correlation between the increase in temperature in the last 100 years and the increase in carbon dioxide concentration in the atmosphere. So the two phenomena seem correlated. Now, of course, someone, for example, Trump denied this kind of correlation, but most of the scientists all around the world, they seem to agree on this. There is a very strong correlation. So it seems logical to think about that the increase in carbon dioxide in the atmosphere has led to global warming. So how can we avoid global warming? Can we reduce the heating of the planet Earth? Basically by reducing the carbon dioxide concentration in the atmosphere. How can we reduce the carbon dioxide concentration in the atmosphere? Well, basically two ways, just to simplify. There was an interesting discussion of a colleague of yours on Saturday about this topic, the degrees. There was a student who has done a degree on this, basically on the global warming, so it was quite interesting. But basically, the way, if we have to reduce the carbon dioxide concentration in the atmosphere, we have two ways. One way is to reduce the emission of carbon dioxide. For example, by using less the cars, by burning less fossil fuel and so on. Which means to slow down our economy, or at least to change the way that we live. Okay? So to reduce the carbon dioxide emission. The other way, equivalent, is to plant more trees. Why? By planting more trees we can reduce the carbon dioxide concentration, because as the trees grows up, it's going to displace the CO2 from the atmosphere into the tree. If you want, a tree can be considered as a carbon sink. So by planting more tree, we are moving the carbon dioxide from the atmosphere into the tree. This is the reason why we said that we shouldn't burn forests, like what's happening now in Brazil, but we should plant more tree, because by planting more tree, we can move the carbon dioxide from the atmosphere into the tree. Okay? Now, why a tree has reduced CO2 emissions? Because the idea is that, think about now the possibility to produce many more timber buildings. So we can, of course, to produce many more buildings, we would have to cut trees. This is not good. But on the other hand, once I cut a tree, I can replant another tree. And only 25 years the tree is ready for harvesting. So the idea is that if I can manage a sustainable forest, something that we can do, because we could say, okay, we have a number of trees, we can cut some of them, not all, we can cut some of them. As soon as we cut one tree, we replant one tree. 25 years the tree is ready. Then I cut another tree, I replant another tree. So basically I can do a sustainable management of the forest in order to make sure that every time I cut a tree, another one is growing. Okay? It's not like cutting all the trees, not what you saw from the television about, for example, the Amazon forest. So they are cutting everything that transforms a forest into an agricultural land. What we are saying is that we cut some trees for use of structural timber into the building, but then we replant immediately another tree. Okay? But if we were able to do this, what could we achieve? We could achieve that we could have a reduction of carbon dioxide from the atmosphere, because this carbon dioxide first will be embodied into the tree, and then will be embodied into the building. So in the end, if we were to increase the number of timber buildings, we would have much more carbon dioxide emission embodied in the building, in the tree, rather than the atmosphere. So we will be able to, in some way, offset the emission of CO2 due to use of cars or due to basically economics activities. Okay? So in this way, we could say that timber is sustainable, because it basically embodies the CO2 inside the material itself. What is that? When you construct a reinforced concrete building, you need to burn some CO2 in order to produce the concrete, to produce the cement. For example, to produce the cement, you need to heat a lot the stones. You heat to 1,000 Celsius degree. To heat to 1,000 Celsius degree, you need to burn material in the end. You need to consume energy. Last thing, reduce embodied energy. So, we can prove that the energy needed to build a timber building is less of the energy needed to build a reinforced concrete building. So in other words, all the operations that we need to do, cutting of the tree, cutting of the boards, producing the panels, and building a building with these panels, is less energy intensive than the construction of a reinforced concrete building or the construction of a steel building. Okay? So for all these three reasons, we could say the wood is a sustainable material. This is a huge advantage. In fact, very often you will see that architects or also some clients, not very often, sometimes, architect and client, they want to use the material wood rather than the other material because it's sustainable. Okay? Any doubts about these 3 points here that you're going to see with more details later on, but now I just wanted to at least to fix the most important concepts. Okay, hygroscopicity. Why is an advantage? Okay, we say the wood breaths, so it can absorb excessive air humidity and return it later to the environment. So in this way, it can act as a sort of reservoir to reduce the humidity fluctuation ensure a dry environment. So the idea is that if you have a wood structure, you are in an environment, suppose that, for example, you have a sauna inside, so you start producing lots of vapor. If you have enough wood, the wood is able to, in some way, to suck, let's say, some of this vapor, some of this humidity inside, in order to make the relative humidity a little bit lower in the environment where you are. Instead, if the environment is very dry, is able to return some of this humidity into the environment by keeping in some way the kind of constant, or let's say not so variable climatic condition in the environment. So in this way, for the user, hygroscopicity of wood is an advantage. Okay? For the wood itself, for the structure, of course, it's not an advantage. It would be better to have a material which doesn't exchange moisture content, because as we saw, exchange of moisture content is going to affect the mechanical properties. Okay? So basically, in this way we can ensure a healthy indoor condition, no mold, and the well-being in a timber building. Thermal insulation, good as, let's say, good thermal insulation properties, which contribute to reduce the primary consumption of energy of the building. So since wood is an insulating material, we will have to spend less energy to heat the building and less energy to cool down the building itself, because it's a more thermal insulator. Okay? And this is another advantage. Of course, due to this property, wood appears as a dry and warm material when touching it. You know very well that since wood is an insulating material, when you touch it, it seems warm. Instead, if you touch a piece of steel, it seems cold. The temperature is the same, but one seems warm and the other one seems cold. Why is that? Because wood is an insulator, so it doesn't absorb lots of the energy of your fingers, because it's an insulator. Instead, steel, which is an excellent conductor, is going to suck immediately your energy, and so you feel it is cold. Okay? While instead, the temperature is the same. The other important thing, if you have a very big timber panels, for example, cross-slab panels, then you can get also an appropriate thermal mass. Thermal mass is a very important property if you want to reduce the amount of energy. So if you want, let's say, to keep more constant the environment inside your building, irrespective of what is the environment outside. So basically, we need thermal mass in order to reduce the thermal fluctuation that we have outside, in winter or summer. If we have a thermal mass, we can reduce this thermal. We have a kind of thermal inertia, if we can reduce this kind of thermal fluctuations. And the X-ray system is going to provide this thermal mass. Okay, now it comes more to the properties, the mechanical properties, the one that we are mostly interested in this course. Tensile compression strength. We saw that wood has got good tensile and compression strength parallel to the rain. The best properties for a solid wood, if you remember, is compression parallel to the rain. It's better than tension. But anyway, both of them are more or less, not the same, but they are comparable. This means that unlike other materials that we have already studied, like concrete, for example, but also masonry, which have quite significant difference between the compression strength, which is very good, and the tensile strength, which is very bad, which means that the material like wood can be used without any reinforcement for beams, columns, truss system, for any sort of structure. Instead, if you remember, reinforcement could be used alone just for columns, not for beams. For beams, it had to be coupled with reinforcement in order to create reinforcement. For wood, we don't need to couple with any other material. We don't need to use a reinforced timber. Timber itself, since it's got both properties, compressive strength and tensile strength, can be used also for beams without any problem. And this, of course, is an advantage. Now let's now go to check some of these properties and to do a comparison between timber and the other two materials that we know better, concrete and steel. You see, we do a comparison considering different properties. We start, the first property is what we are calling the permissible stress. Permissible stress, if you remember, it's basically the strength divided by a global safety coefficient. It's a measure of the strength. So the permissible stress is basically a measure of the strength of the material. Okay? Now, first comparison that we can do is between the strength, the compressive strength of timber and the compressive strength of concrete. If we have a look, they are both more or less the same. So timber and concrete have more or less the same compressive strength, 10 megapascal. What does it mean that they have the same compressive strength? It means that if you are going down to this article, if you see, here you can see a very nice column made of reinforced concrete. Now, if I wanted to ask you, how would be this column if it was built out of timber? What would you answer me? If I want to rebuild this column out of timber, which kind of pressure of cross-section would I expect to get? Is the question clear? Do I need to repeat it in Italian? Repeat. Se dovessi ricostruire questa colonna qui fatta di legno, che sezione dovrei utilizzare? Non lo stesso. Exactly. It would be exactly the same. Why? Because the permissible stress is the same. Very simple. Very simple but not trivial, because if you think about, without having this kind of information, if I were to ask you, okay, a column like this made of timber, how would it be? Larger or smaller or the same? You probably would have thought it would be larger, because the idea is that wood is less strong than concrete. Instead, you see they are more or less the same. You see, column. Suppose that I have to design a column for 1000 kilonewton. The formula in order to get the minimum cross-sectional area is P divided by permissible strength. So for timber I will get 1000, so 33 by 33, and for concrete 1000, 33 by 33. So once you see a reinforced concrete structure with a certain size, you can immediately have an idea about the size of the same structure made of wood. The size will be more or less the same. The same also for a timber beam, would be more or less the same. If you see a timber reinforced concrete beam with a certain size, if you were to rebuild the same reinforced concrete, the same beam out of timber, in the end, more or less the cross-section would be the same. So, the timber structure is, I would say, as bulky as a concrete structure. Reinforced concrete structure is what we call in Italian struttura tozza, bulky. Timber, more or less same size. Then we have a look to steel. The permissible stress of steel is 160 megapascal. Now, if I had to rebuild this column out of steel, what kind of cross section could I expect? Smaller. How many times smaller? 60. The ratio between the two permissible stress. Okay. So the cross section of a steel column would be 16 times smaller compared to the cross section of a timber and a reinforced concrete structure. In fact, steel structure are usually considered as a slender structure. Struttura è slender. So cross section smaller as relative also to the length. So we will conclude that timber and reinforced concrete structure are squat structures. Strutture tozze. Steel structures are slender structures. Strutture slender. The ratio between the two is 16, more or less. Okay? Good. Now, if this is clear, let's go now to calculate the weight of these three columns. The reinforced concrete column, the timber column, and the steel column. What is the weight of those three columns? Well, to calculate the weight, we need the volume, and we need the unit weight. Unit weight of timber, on average, is 500 decanewton per cubic meter. The unit weight of steel is 7,850 decanewton per cubic meter, and the unit weight of concrete 2,500 reinforced concrete. Okay? So we see immediately that there is a ratio of 5 between the unit weight of concrete and the unit weight of timber. Before we said that the column made of timber is the same cross section as the column made of reinforced concrete. So also the volume is the same. How will be the weight? So the less. 5 times less. So the weight of the timber column will be 5 times less than the weight of the reinforced concrete column. What does it mean? It means that both structures, we said before, are bulky structures, squat structures, strutture tozze importanti, but the strength, the weight of the timber is only 1/5 of the weight of the concrete. 1/5 is much less. Okay? Good. Now, let's have a look now to the steel column. The steel column, we said before, is 16 times smaller in volume also than the reinforced concrete column, the timber column. However, you see that the unit weight of steel is how many times larger than timber?
Less than 16.
Less
than 16.
More or less 16. More or less 16. So, we have a volume 16 times lower with a material which density is 6 times higher. So in the end, the two effects cancel out. In the end, we get that the weight of the steel column is more or less the same as the weight of the timber column. Okay? We can do this calculation very simple here. Weight, you see, WA times gamma M, 50 for timber, 49 for steel, 240 for concrete. So what we discovered in the end? We discovered that steel structures and timber structures can be regarded as lightweight structures. Instead, reinforced concrete structure and masonry structure, we don't discuss about masonry, but masonry is the same. Reinforced concrete structure, masonry structure, instead they are heavy structures. Because we see that the weight of a reinforced concrete structure is 5 times higher than the weight of a steel or timber structure. Okay? First important result. Second important result, in terms of geometrical appearance of the structure, timber structures and reinforced concrete structures are squat, bulky structures. They are important structures. While instead, steel structures are slender structures. So, if you get a question from an architect about having a structure which is almost invisible, I remember when I was teaching at the Faculty of Architecture in Sardinia, very often some students for their degrees or anyway, they were asking that they want to do an almost invisible structure. And they were asking, can I do an almost invisible, of course not invisible, a structure that are not very important, they cannot see so much. Can I do an almost invisible structure out of timber? If they ask you this question, what do you have to answer to that? Can they do an almost invisible structure by using timber? No. Why not? The timber structure are very big. Okay? So if your client wants to do an almost invisible structure, you need to tell, look, you can't use timber, you can't use reinforced concrete. The only thing you can use is metals, aluminium or steel. Or if you want to use concrete, you use high performance concrete. Concrete with a strength which is 10 times the strength of normal concrete. And you can do the thickness. Okay? It's clear. This is very important because, of course, when you do the design, the conceptual design of a building, you need to make aware the architects that some things are possible, some are not. You can't have a very slender structure made of timber. It's impossible. Okay? You need to do other materials. So in the end, we said that timber structure, exactly like steel structure, in this respect there is no difference between timber and steel. They are both lightweight structure. Their weight is more or less the same. The most important difference is that the steel structure are slender, timber structures that are squat, are much more important. But the weight is the same. Okay? Now, let's think about advantages and disadvantages of having a lightweight structure. What is the advantage of having a lightweight structure? So having a structure made of steel or timber, as we said, the weight is 1/5 of the same structure made of reinforced concrete. Which advantages we can find? Transportation construction, for sure, because we can prefabricate modular elements, timber, so for example, a beam, a column, a wall, which would be very lightweight, so we can transport much easily, and we can erect also the building much easier. Compared, for example, to a precast concrete construction, where the timber, beam, and column, they weigh 5 times the one of timber and steel. So transportation and erection, for sure, are advantages of easy transportation and erection, are advantages of lightweight structure. Other advantages.
The action lower.
The
action on the structure.
Okay, which actions of the structure will be lower with a lightweight structure?
All gravitational.
Okay, gravity, which means permanent loads. Permanent loads, of course, which depends on the structure self weight, will be lower for a lightweight structure. 5 times lower. Important advantage. And so which means also the bending moment, everything will be lower.
And also, for example, horizontal action due to the earthquake.
Okay, yes. Another huge advantage is the seismic action. The seismic action you learn in the course of reinforced concrete design with Professor Di Fabio. The seismic action is proportional, roughly speaking, is proportional to which quantity? The seismic action. To the weight. It's proportional to the weight. So having a lightweight structure, a structure which is 5 times lighter than another, means that also the seismic action will be 5 times lower. Okay? Huge advantage of a lightweight structure, that the seismic action much lower, 5 times lower compared to reinforced concrete. Okay? Other advantages of a lightweight structure related to the lower gravity. But this lower gravity load must go down eventually to the foundation. So since I have also to design the foundation, I have also to check the ground which is underneath the foundation. Obviously, if I have a lightweight structure, also the stresses in the foundation will be 5 times lower. Also the stresses in the ground will be 5 times lower. So you would say cheaper and easier foundation systems for a lightweight structure. Okay? Okay, now, possible problem we would like to frame with lightweight structures. It's always an advantage to have a lightweight structure. Well, we said before, if you are in an earthquake-prone area, if you are here in L'Aquila, for sure it's better to have a lightweight structure, also in Turkey, of course. It's better to have a lightweight structure than a heavy structure. However, if you are based in the middle of the Mississippi, in the US, in the middle of the flat, maybe there, have a lightweight structure may not be an advantage. Why? Because there is a problem of the wind. The effects of the wind. Wind, you know the effect of the wind, you have a pressure on one side, we have a suction on the other, and on the roof, usually, unless you have a very steep roof, you have suction on the roof. So, if you have a lightweight structure, it may happen that the uplifting force due to the wind is higher than the resistance given by the gravity, so by the self weight of the roof itself. So in the end, you can get this kind of situation. You can see you can have some unroofing. Basically because the wind, usually in a reinforced concrete structure, the uplift of the wind is basically counterbalanced, more than counterbalanced by the self weight of the block. Okay? Instead of the lightweight structure like this, timber, but also a steel structure, the self weight of the roof cannot counterbalance the uplifting due to the wind. Okay? So unroofing could be a problem. And then we have another problem. The other problem is due to the important effect of snow. If you have a lightweight structure, basically, it's much easier than if you have an exceptional event, like a very high of snow, you get to a situation where you get to the failure of the roof. While instead, if the same roof is made of reinforced concrete, even if you have an exceptional meteorological event with maybe a couple of meters of snow, usually the roof made of reinforced concrete doesn't fail, does not collapse. Why is that now? Basically, due to if you have a lightweight structure, you have a very high value of Q, which is basically the variable load over self-weight. And in this case, there are only few safety margins when you have an increase in Q with respect to the design value. Now, let's try to understand why is that. So why may snow become critical for lightweight structures? Suppose that you are going to design a one-way roof structure, just to simplify. So, there will be, for sure, there will be a number of beams, and the design inequality for a one-way roof structure will be something like this. The bending moment demand due to the load condition at artifact state shall be lower than or equal to the bending moment capacity. Bending moment capacity, in general, now forget about K mod and K depth. For a normal material, bending moment capacity is the design stress, which is the characteristic strength, characteristic bending strength divided by the partial safety factor, times the section modulus of the beam. If you have an elastic material, the section modulus for a rectangular cross section is the breadth times the depth squared divided by 6. Okay, BD squared divided by 6. Okay, so this is the design inequality for a one-way roof structure subjected to bending. Now, at ultimate state, the load condition is the self-weight, permanent load, times the partial factor gamma G, plus the variable load, so the snow load, times the partial factor gamma Q. Okay? These factors are gamma G, if you remember, is 1.3 according to the Italian regulation, 1.35 according to the Eurocode. Gamma Q is 1.5. Now, for the sake of simplicity, let's make this approximation. Let's assume that gamma G is more or less the same as gamma Q. That 1.3 is equal exactly to 1.5. And also, let's assume that gamma M, the partial safety factor, like in the case of solid timber, is equal to 1.3. What can we do? We can write that since in the structural analysis we usually do a linear analysis. If you remember, we do the plastic analysis only when calculating if the material is plastic, we use the plastic analysis only for calculating the capacity. For timber, we will not even do a plastic analysis here, because we will consider timber as an elastic material. But for input concrete, when it comes to calculate the capacity, the bending capacity, you remember we've done the plastic analysis to calculate the stress drop into the concrete and then the plasticization into the material. But when we do the structural analysis, we always do an elastic analysis. In sub 2000, we've done an elastic analysis of the frame, right? So, since we do an elastic analysis, we can say that the bending moment demand due to the ultimate limit state can also be considered as a gamma Q times the bending moment demand due to G plus Q. So we have done this approximation. We say, okay, gamma G is equal to gamma Q. So we could say Fu is equal to gamma Q times G plus Q. And since we do a linear analysis, gamma Q can be taken outside the parentheses. Okay? It's clear? So, the bending moment demand due to the ultimate limit state is equal to gamma Q, 1.5, times the bending moment demand due to G plus Q. Permanent plus variable without any partial factor. Okay? It's clear so far? Okay. And now, look at this design inequality. We said that MED can be written as gamma Q times MED as a function of G plus Q. So this one is not MED times. This is MED as a function, okay, not times. So gamma Q times MED as a function of G plus Q must be less than or equal to FMK divided by gamma M times WY. So what I can do, I can divide it by gamma Q. If I divide by gamma Q, then you see MED as a function of G plus Q shall be less than or equal to FMK divided by gamma Q times gamma M times WY. Okay? Now, if you do 1.5 times 1.3, you get 1.95, which is almost 2. So in the end, you see that the design inequality is that the bending moment demand due to the sum of the permanent and the variable stop load shall be less than or equal to the section modulus WY times FMK, characteristic strength of the wood, of the material, divided by 2. Clear? Okay, what does it mean this? If I want to get to the actual failure, so in which situation we will get the actual failure of the roof? To get to the actual failure of the roof, I need to reach FMK. Under the load G plus Q, as you can see, we are far away from the actual failure. Because from G plus Q, we have a capacity given by, if you know, this is the actual capacity, divided by 2. So FMK is the actual characteristic strength. Once you get to FMK, then you get a failure. But under G plus Q, you get only, you see, 2/2 of the characteristic strength. So you are far away from the first actual failure. Okay? So in order to get the failure, which value of load should I apply? So here's a global safety factor of 2 against the actual failure. So the maximum increase in the variable snow load before the actual failure takes place. Now I want to calculate what is the maximum increase in variable load, so snow load, such that my structure reach the actual failure. So reach FMK, not FMK divided by 2. So delta Q, basically if under a load G plus Q, I have a safety coefficient of 2, so I'm at a stress level which is half the actual value that leads to collapse. In order to get to the actual failure, I will have to double up G plus Q. Okay? If I double up G plus Q, so I get to 2 times G plus Q, then I will get here the actual failure. So, assuming now that the permanent load is given, it's the same way, we cannot change it, we are interested in understanding which is the increase in snow load, delta Q, which leads to the actual failure. as we said before, Q, the design snow load, doesn't take the structure to the actual failure. It actually, with this value here, we have a safety coefficient of 2. How much can we increase Q in order to get to the actual failure? Well, delta Q shall be given by the total failure load. So the total failure load, if G plus Q leads to a safety coefficient of 2, the total failure load will be twice G plus Q. So 2 times G plus Q is the total failure load, minus G plus Q is the actual failure load. So this difference will give me the increase in snow load that my structure can tolerate before it fails. Okay? This value is 2 times G plus Q minus G plus Q is G plus Q. So I can increase the snow by G plus Q in order to get to the actual failure of the structure. Okay? Now, let's consider 2 different cases. First case, the case of a heavy structure. So a structure made of reinforced concrete. Okay? For example, a structure, if a roof is made of reinforced concrete, G, permanent load, could be something like 8 kN per square meter. And the design load, the snow load, could be 2 kN per square meter. This is a heavy design load. Here in L'Aquila, I think we are about 90. Well, it depends on the level anyway. Maybe here 1,000 meters would be also 2. Okay, so G, permanent self-weight of the reinforced concrete roof, 8 kN per square meter, and design value of the snow, 2 kN per square meter. So if you have a heavy structure, you can see that the ratio between the variable load and the self-weight is fairly low, is 1/4. Okay? Now in this case, let's go to calculate the delta Q. Delta Q, so the increase in snow load that this structure can tolerate, is G plus Q. Remember, before we found out delta Q is G plus Q. So, if we replace the number inside, delta Q is 10 kN per square meter. So this roof made of reinforced concrete can resist up to 10 kN per square meter of snow. So this could be something like 4 or 5 meters of snow, even more, before it fails. So you see, delta Q, the increase in variable load divided by the design value load, is 10 divided by 5 times. So a heavy reinforced concrete roof can resist up to 5 times the design snow load. And you can understand why, when there is an exceptional snowfall, hardly ever you have a bout of reinforced concrete floor or roof that collapse due to the snow. I never had something like this. Usually you have about steel floors or timber floors that collapsed, timber roofs that collapsed because of the snow. And now we understand why. Because you see, with a reinforced concrete, you have a safety coefficient in terms of snow of 5 times the design load before you take the failure. Consider now a lightweight timber roof. In this case, in a lightweight timber roof, the self-weight of the structure is more or less the same as the weight of the variable action. So self-weight of the structure 2, self-weight of can be sometimes even lower. Let's say 2, and the snow load 2. So this time Q over G is 1, not 1/4 like before. And delta Q, G plus Q, is 4 kN per square meter. So delta Q over Q, you see this time, rather than having a factor of 5, we have a factor of 2. So when we design a lightweight roof, we have a safety coefficient respect to the, let's say, exceptional snowfall of only 2, no longer 5 like before. So it means that if you have a heavy snowfall, rather than 2, 4, up to 4, we get to the failure. Okay? This should clarify why, for lightweight structures, or let's say lightweight structures, are much more sensitive to any increase of the variable actions with respect to the design limit. While instead, heavy structures are not much sensitive to this. Okay? Clear? Okay, speed of erection. This is another very important advantage of wood structures. Wood construction is a highly prefabricated type of construction. So basically, all the components, beams, columns, walls, are prefabricated on site. And then they come to the building site, they are erected, they are lifted, they trained to the position, they are connected. In any case, we have a dry kind of construction. So we don't have to wait for curing and hardening of concrete this time. We have no formworks and props. If you remember, to construct a reinforced concrete floor, you need to put some props. You need to leave the props there for theoretically 28 days, and you can leave them, you can put them out. For a timber, you see, you put your walls, then you arrive with your timber panel, you screw them down. In few hours, you can get your floor ready. Only few hours. We have also the ease of handling due to the lightweight of the panels, and as I said before, possibility to prefabricate everything off-site by reducing the work on the building site to a minimum, only minimum amount of work. So basically we displace most of the work from the building site to the prefabrication plant. This way also avoiding problems with injuries on the building site. It's much safer to work in a warehouse than on the building site. Okay. Any question on the timber advantages that we saw before? I think it's a good time now to have a break before starting the discussion on the disadvantages of timber. I would say we have 15 minutes, so we can start again at 10 past, okay, let's say 15 past 5. Okay? Thank you.